Hi, good morning. Today we are going to start one definition, the best approximation to a vector in W. Okay, a best approximation to beta by vectors in W is a vector alpha in W such that norm of beta minus alpha is less than or equal to norm of gamma minus alpha for every gamma belongs to W. So, a best approximation to beta by vectors in W is a vector alpha. Okay, this 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 alpha is a best approximation to beta only if satisfies this condition. That is, norm of beta minus alpha is less than or equal to norm of gamma minus alpha for every gamma belongs to W. Okay. For every 1 minute. Okay. So this is our definition, best approximation. That means actually in terms of distance between beta and alpha is less than or equal to distance between gamma and alpha for every gamma belongs to W. Now moving to one of the most important theorem. All these results are very important. If W is a subspace of an inner product space V and let beta be a vector in V. Listen carefully. Let W be a subspace of an inner product space V. Clear? And beta is a vector in V. The vector alpha in W is a best approximation to beta by vectors in W if and only if beta minus alpha is orthogonal to every vector in W. What is the first statement? Listen carefully. W is the subspace of A. Suppose this is our space V and W is the subspace of a inner product space V and beta be a vector in V. A vector alpha in W is a best approximation to beta by vectors in W if and only if beta minus alpha is orthogonal to every vector in W. That means inner product of beta minus alpha and any vector some gamma equal to 0 for every gamma belongs to W. This is what we have to prove. Clear? And this result we will use this result through for proving these two results. Okay, also we are using this throughout our last session. Okay, throughout this section. Now I will prove the first one. What about the second one? If a best approximation to beta by vectors in W exists, then it is unique. The best approximation is unique. And the last result, if W is finite dimensional and alpha 1, alpha 2, etc. alpha n is an orthonormal basis for W, then the vector, this vector, alpha equal to sigma over k inner product of beta and alpha k divided by norm of alpha k square into alpha k is the unique best approximation to beta by vectors in W. This is what we have to prove. Okay, clear? I will repeat the statement. If W is a subspace of an inner product space V and let beta be a vector in V. And we have to prove the first one. Alpha is a best approximation to beta by vectors in W if beta minus alpha is orthogonal to every vector in W. We are going to prove that one. So that is an if and only if statement. So first we assume alpha is a best approximation to beta, and we have to prove beta minus alpha is orthogonal to every vector in W. Conversely, assume that beta minus alpha is orthogonal to every vector in W, and we have to prove alpha is the best approximation to beta. So for proving this, first you take some any vector gamma in W. Beta is a vector in V, and for any vector beta in W, what is beta minus gamma? Beta minus gamma you can write as beta minus alpha plus alpha minus gamma. Add and subtract alpha. Okay, so norm of beta minus gamma square is same as norm of beta minus alpha plus alpha minus gamma whole square. And we know that inner product of beta, norm of alpha plus beta whole square is norm of alpha square plus 2 times real part of alpha and beta plus norm of beta square. So we apply this result here. Okay, so norm of beta minus gamma square is equal to norm of beta minus alpha square plus 2 times real part of inner product of beta minus alpha and alpha minus gamma plus norm of alpha minus gamma whole square. We are using this result here. Clear? Hope it is clear. Now first assumption, assume beta minus alpha is orthogonal to every vector in W, and we have to prove alpha is the best approximation to beta. That means we have to prove norm of beta minus alpha is less than or equal to norm of gamma minus alpha for every gamma belongs to W. So let gamma be any vector in W. Then alpha minus gamma belongs to W because alpha belongs to W and gamma belongs to W. W is a subspace, therefore alpha minus gamma belongs to W. Since beta minus alpha is orthogonal to every vector in W, beta minus alpha is orthogonal to alpha minus gamma also. Okay, alpha. Beta minus alpha is orthogonal to every vector. So alpha minus gamma belongs to W. So beta minus alpha is orthogonal to alpha minus gamma. So inner product of beta minus alpha and alpha minus gamma equal to 0. So norm of beta minus gamma whole square is equal to this term is plus 2 times a real part of this term becomes 0. So norm of beta minus alpha square plus norm of alpha minus gamma whole square. So from this result, each term is positive. So this term is greater than or equal to norm of this term. This is a norm, therefore this is greater than or equal to 0. This plus this is equal to this one. That means this term is greater than or equal to norm of beta minus alpha whole square. As gamma is arbitrary, we get norm of beta minus gamma whole square is greater than or equal to norm of beta minus alpha whole square for every gamma belongs to W, and we get norm of beta minus alpha is less than or equal to norm of beta minus gamma because we are taking positive root. Okay, a norm is always positive. Therefore, norm of beta minus alpha is less than or equal to norm of beta minus gamma for every gamma belongs to W. That means, what is the meaning of that? This means alpha is the best approximation to beta by vectors in W. Okay, therefore if beta minus alpha is orthogonal to every vector in W, then we get alpha is the best approximation to beta in W. Clear? The converse part, assume that alpha is the best approximation to beta by vectors in W, and we have to prove beta minus alpha is orthogonal to every vector in W. Okay. So by definition, we get norm of beta minus alpha less than or equal to norm of beta minus gamma for every gamma belongs to W. Squaring this, we get this one. Norm of beta minus alpha whole square is less than or equal to beta minus gamma. For beta minus gamma, we are replacing beta minus alpha plus alpha minus gamma. And this is norm of beta minus alpha whole square plus 2 times real part of beta product of beta minus alpha and alpha minus gamma plus norm of alpha minus gamma whole square. Okay, this is from the result of norm of alpha plus beta whole square. Okay, From here, you can cancel norm of beta minus alpha whole square, and we get 2 times real part of inner product of beta minus alpha and alpha minus gamma plus norm of alpha minus gamma whole square is greater than or equal to 0. Okay. So now next time you have to uh, listen carefully. Note that every vector tau in W can be expressed in the form alpha minus gamma with gamma in W. If you take any vector, so for example, alpha is fixed. Oh, in set of all real numbers, minus 3, minus 2, minus 1, 0, 1, 2, 3, etc. This is set of all real numbers. And I am fixing some alpha is equal to some 2. And tau is equal, if tau equal to some 5. Okay. And this 2 you can write, this 5 you can write as 2 minus 3, and you can take gamma equal to minus 3. That is alpha is 2, gamma is minus 3, and this 2 5 you can write as alpha minus gamma. Or if you take some tau equal to some minus 3 and alpha equal to 2, so you can take minus 4, alpha equal to 2, then you can write tau as 2 minus 6 and gamma equal to minus 6. So every vector, as W is a subspace, we can write like this for any vector. So for every vector tau in W can be expressed in the form alpha minus gamma with gamma in W. So this result is true for alpha minus gamma, we can replace it by tau. Clear? So 2 times real part of inner product of beta minus alpha and tau plus norm of tau square is greater than or equal to 0. So you can take any tau that belongs to W. Okay. So in particular, if you take tau as minus inner product of beta minus alpha, listen carefully. We are taking tau is equal to inner product of beta minus alpha and alpha minus gamma divided by norm of alpha minus gamma whole square into alpha minus gamma. This part beta minus alpha, so inner product of beta minus alpha, and all remaining term is alpha minus gamma. Alpha minus gamma divided by norm of alpha minus gamma whole square into alpha minus gamma. We are taking tau as this one. Once again I am repeating. Finally we get this one, 2 times real part of inner product of beta minus alpha and alpha minus gamma plus norm of alpha minus gamma whole square is greater than or equal to 0, and this is true for any tau. Okay, as it is because any tau belongs to W, you can write in the form alpha minus gamma. Therefore for alpha minus gamma, we are replacing alpha minus gamma by tau. So 2 times real part of beta minus alpha and tau plus norm of tau square is greater than or equal to 0. Now this tau is not alpha minus gamma. We uh, uh, this result is true for any vector alpha minus gamma, and every vector tau in W you can express in terms of alpha minus gamma. Therefore, this result is true for any vector tau in W. Okay. So in particular, this result is true for if you take tau equal to this one. Clearly, this is an element in W because this is an inner product and this is norm. Therefore, this is a scalar quantity and this is a alpha minus gamma, and alpha minus gamma belongs to W, and this is actually a scalar multiple of alpha minus gamma. Therefore, this also belongs to W. Therefore, this result is true for this tau also. Clear? Now, what is inner product of beta minus alpha and tau? Inner product of beta minus alpha and this one. and this is a scalar quantity, and you can take this outside, and this is in second part, therefore there will be a conjugate. Okay, and finally we get inner product of beta minus alpha and alpha minus gamma. If you look at these two terms, this is actually these are same. This is here, there is an also an inner product. Okay, so this is a same, this is of the form minus set conjugate set is mod set square, so mod set square minus inner product of minus modulus of inner product of beta minus alpha and alpha minus gamma whole square divided by norm of alpha minus gamma whole square. Okay, now what about real part of set? Real part of set is if z is equal to x plus I y. What about mod set? Mod set square is x square plus y square. So mod set is also okay. So what about real part of mod set? Real part of mod set is same as mod set. Sorry, mod set. So if you take 2 times the real part of this one, what we will get? Minus 2 times real part of this term is same as this term. Therefore, we will get this one. Okay. Now, if you look at next term, norm of tau square, that means inner product of tau and tau. That is like this. And this is a constant, you can take outside, and minus minus plus, and this is in the second part, therefore there will be a conjugate. So inner product of norm of alpha minus gamma and alpha minus gamma, that's equal to norm of alpha minus gamma whole square. We cancel each other and we get norm of inner product of beta minus alpha uh, and alpha minus gamma whole square divided by norm of alpha minus gamma whole square. This is equation 3. From adding 2 and 3 we get this one. Okay, but there is a negative sign, therefore if you multiply throughout by negative sign, we will get this is less than or equal to 0. What about the denominator? Denominator is always greater than 0, and therefore this is less than or equal to 0 means numerator is less than or equal to 0. What about the numerator? This is a modulus. Therefore, this is less, modulus value is always greater than 0. Therefore, this is less than or equal to 0 means that term must be equal to 0. That is modulus of inner product of beta minus alpha and alpha minus gamma is equal to 0. That means inner product of beta minus alpha and alpha minus gamma equal to 0. Okay, so if you take any tau, what we get in a product of beta minus alpha and a tau equal to 0 for every tau belongs to W, but because we know that alpha minus gamma for any vector tau in W, we can write tau as alpha minus gamma. Therefore, in a product of beta minus alpha and a tau equal to 0 for every tau belongs to W. That means in a product of beta minus alpha is orthogonal to every vector in W. Okay. Now moving to second problem. It is very simple. We have to prove the best approximation is unique. So we are taking two best approximation, alpha 1 and alpha 2, and we have to prove alpha 1 equal to alpha 2. As alpha 1 and alpha 2 are best approximation, by the first result, beta minus alpha 1 is orthogonal to every vector in W, and beta minus alpha 2 is orthogonal to every vector in W. So each term is equal to 0. That means beta minus alpha 1 over gamma, and inner product of beta minus alpha 2 and gamma. Inner product of beta minus alpha 1 and gamma minus inner product of beta minus alpha 2 and gamma equal to 0. And splitting this, we get inner product of beta and alpha minus inner product of alpha 1 and gamma minus inner product of beta and gamma plus inner product of alpha 2 and gamma equal to 0. Cancelling these two terms, we get inner product of alpha 2 and gamma minus inner product of alpha 1 and gamma equal to 0. And from this, we get inner product of alpha 2 minus alpha 1 and gamma equal to 0 for every gamma belongs to W. And finally, what we get, this is inner product of alpha and gamma equal to 0 for every gamma belongs to W implies alpha must be equal to 0. That means alpha 2 minus alpha 1 equal to 0. That is alpha 2 equal to alpha 1. Therefore, if the best approximation exists, then it must be unique. And the last problem, we have to prove that alpha 1, alpha 2, etc. alpha n are orthogonal basis of a W is a finite dimensional vector space. Then we have to prove alpha equal to this one is the best approximation to beta. Listen carefully. Alpha equal to in sigma k equal to 1 to n inner product of beta and alpha k divided by norm of alpha k whole square into alpha k. This is the best approximation. We have to prove this is the best approximation. For proving this is the best approximation, we have to prove inner product of beta minus alpha is orthogonal to every vector in W. That means we have to prove beta minus alpha is orthogonal to, that means inner product of beta minus alpha and gamma equal to 0 for every gamma belongs to W. So for this, it is enough to prove that given alpha 1, alpha 2, etc., alpha n is a basis. Okay, so it is enough to prove that beta minus alpha is orthogonal to every element in the basis. That means inner product of beta minus alpha and alpha j equal to 0 for every j equal to 1 to etc. n. This is what we have to prove. Since W is a subspace spanned by orthogonal vectors, it is enough to prove beta minus alpha is orthogonal to alpha j for every j equal to 1 to etc. n. So consider this one, and this is the substitute in the definition of alpha. We get this one in a product of beta and alpha j minus sigma. Okay, so I am expanding the sigma k equal to, suppose k equal to 1. K equal to 1, this become inner product of beta and alpha 1 by norm of alpha 1 square into alpha 1. Okay, and simplifying this, we get inner product of beta and alpha 1 divided by norm of alpha 1 square into alpha 1 and alpha j, and this one alpha 2 and alpha j, etc. And here all the terms are 0 because alpha j's are orthogonal. Therefore, remaining term is inner product of beta and alpha j into inner product of alpha j and alpha j divided by norm of alpha j square. Cancelling these two terms, we get inner product of beta and alpha j minus inner product of beta and alpha j, which is equal to 0. Therefore, beta minus alpha inner product of beta minus alpha and alpha j equal to 0 for every j equal to 1 to etc. And that means beta minus alpha is orthogonal to every vector in W. This implies alpha is the best approximation to beta by vectors in W. Okay, hope everything is clear. That's all for today's class. Okay.